we talk about graphs of linear motion, well, things move, okay, they move. And how do we measure their movement? Well, we measure it in, say, meters per second. That implies that time is very important. So time is the horizontal axis in distance time graphs, although those are rare. It's usually position or displacement time. Because after all, the total distance you cover is not quite as important as where you start and where you end up. We also use time for the horizontal axis in velocity time graphs, and, well, when we measure the acceleration, that's the slope of the velocity time graph's curve at some time. And then, well, what about the next bit of time? And the next bit, and the next bit. Well, okay, now the acceleration, well, we measure it at particular moments. So the slope of the velocity time curve at particular moments is what we're looking for. Hey, so what about the next moment over and the next and so on? So therefore, the horizontal axis is still time. And the vertical is then, of course, acceleration. These describe the motion of an object. And, well, this axis, acceleration, is in meters per second squared. And if no direction is specified, then it's positive direction. And whether or not you count it as a vector is almost philosophical. And the time is here in seconds, as is standard. Now, what does the area under the line or the curve represent? Well, we know that acceleration is equal, well, on average, is equal to the change in velocity divided by change in time. So what happens when we multiply the acceleration by the time to find the height of, say, a rectangle? Well, we get the change in velocity there. So what happens if it's a curve? Well, then we can have an infinitely large number of infinitely narrow rectangles, and that will give us the total change in velocity. What does that also give us? It also fills up the whole area under the curve. But that's calculus, and we can do that rather later. Right now, we're in grade 11 physics, so we don't do calculus yet. Now, we usually use initial velocity and initial position or displacement of 0. Why is this? It's because if you look at this velocity time graph, you see that the velocity increases by 10 meters per second per second. There's a problem here. If we're dealing with this line, what if we draw a parallel line that also has a slope of 10 meters per second per second? Well, then that's going to be the same acceleration time graph. And that's why you need some value somewhere to nail it down to a particular velocity time graph, like this one, where initial velocity is 0. Now here we have the formulas, which we should be familiar with, and a reminder that the displacement is going to be the area under the velocity time graph plus your initial displacement. Because, hey guys, he moved for 20 kilometers per hour and 2 hours. Okay. Where did he start? Did he start at the reference point? Or did he start already some distance from the reference point? So he's moving down this road, so in that direction, 20 kilometers per hour for 2 hours. Is he 40 kilometers away from the reference, or is he more than that? Or less than that if he began in the opposite direction at a negative initial position or initial displacement? Okay, now what about the position time graph? This is quadratic. This is part of a parabola. Now, technically speaking, you're not supposed to show values past the other end, but graphing calculators sometimes don't let you set boundaries, which is annoying. So what are these axes? This is a position time graph based off of this velocity time graph. Well, we know that time is still the horizontal axis. Time in seconds. And here we have displacement in meters, or position in meters. Okay. What happens if we have to sketch a velocity time graph and position time graph according to an acceleration time graph, given some initial numbers, or it could have been given some values, say, halfway through? Well, we have this acceleration time graph here, and v initial is 10 meters per second. Acceleration is going to be 10 meters per second for 6 seconds. So we go from 10 to 70 at 6 seconds we reach 70, and then we go on a flat line for the rest of the time. Well, I'm going to plot some lines. Since it's not very reliable to draw straight lines with the equipment I have, remember that you should use a ruler. As we can see, using a ruler to do our lines is really nice compared to doing it by hand. Yes, okay, it's true that short lines, most people can use the repeated shading ability with pencils. So start off with a light line and then correct as needed by repeated shading. Yes, most people can get those pretty straight, but it's still much easier to just use a ruler. However, sometimes you really can't quite use a ruler. Now we know that the distance initially is 0. There's not necessarily going to be a unit attached when you say the initial is 0, for hopefully obvious reasons. Okay, so what was our velocity in the first second? Well, we went from 10 to 20 meters per second, and the average was 15. So we end up at, in the general neighborhood of, this is 25, therefore most of the way up. Now we start over here at 0, 0, and the next grid, well, instead of 15, we have 25 as our average, so 20 to 30. And that means going to about here. And the next second, we can observe that we go from 30 to 40, which is 35 more. And that brings us up to 75. 25, 10, that's 35. And the next second is going to be 45, which means we go from 75 to 120. And the next second after that, we go up by 55 to 175. Now, when did we stop accelerating? At 6 seconds, right? So 6 seconds is going to be, so from 5 to 6 seconds, average of 65, because it was 60 to 70 meters per second. So 65 here would be there. And then we go up 70 for every second. And from here, that's 10, and then 50, and then 10 again. That's 15, and 50, that's 65, and then 5 over here. And then off the charts. Now, we could draw ourselves a curve here. However, depending on how much your teacher lets you have leeway, you could probably just use a ruler to connect these dots, and it will be roughly okay if you're just being asked for a rough sketch. So as we can see, for the points that we have to draw a curve through, yeah, you might want a lot of points. But once it gets linear, really, this point here, at 7 seconds, it was kind of unnecessary. We could have just drawn a straight line all the way through with a ruler or similar tool. Okay, as we can see, having equipment do it for us is a lot neater than trying it by hand. Yes, okay, most of us can probably do the light pencil shade exploit for, or whatever the technical term is called for art, in terms of drawing relatively straight lines, but it's still better to use a ruler. Lots faster too. So here we see a parabola, or part of a parabola. That's because the function for displacement is this. Displacement is on the vertical axis, so you can think of this as y equals ax squared, x being t here instead, plus bx, so initial velocity times time, plus c, so wherever you began, as your constant value. So let's do our next example. In this example, we need to draw an acceleration time graph and a position time graph. And here we only give an initial position because the acceleration can be found purely by looking at the velocity time graph. And it's from 0 seconds to 8 seconds, which means this part here we can ignore, which is nice. Okay, so here we start at 10, 20, 30, 40, 45. And we go down to 0 in 3 seconds. So we go negative 45, being our change in velocity, divided by 3. That is, of course, negative 15. And the units are in meters per second, or meters per second squared. So we can do this line by hand. Yeah, sure, we can do this line by hand, but when it's not on a grid line especially, or when it's particularly long, please do use a ruler, even though here we're being kind of expedient. And then there's a problem of, hey, since we recover to the same velocity of 45 meters per second in 3 seconds as well, that's just straight from negative 15 meters per second squared to positive 15 meters per second squared. How do we signify the jump? Well, we use one of these dashed lines. What about here? Well, the velocity plateaued. It went flat line. How do we show that? Well, that's an acceleration of 0. How do we show, though, that we're graphing all the way out to 8 seconds? The general solution is to make it noticeably thicker than the surrounding bits. Well, yes, okay, you could use a different color of ink or pencil, but that's usually a lot of trouble. So yeah, you can guess where that's going. Our initial position is 10 meters. Therefore, we plot 0, 10, which is about here. Now our velocity went from 45 meters per second to 30 meters per second in the first second. The average there is 37.5. So we covered 37.5 meters from 10. And that brings us to just shy of 50. So 47.5. And then what about the next second? Well, 30 to 15, the average is... Well, if we don't want to do calculations with this many decimals, we could always go for the, hey, 45 meters per second initial velocity and 15 final. That averages to 30 over 2 seconds. So that's 60 meters from the initial position of 10 meters, which comes out to 70. So just below 75. Okay, it's a little bit further below than that. And what about the last second? Well, we end up going from 15 meters per second to 0, which means 7.5 on average. And that brings us to 77.5. Now, for the third to fourth second, so that's 1 second, we have 0 to 15 meters per second. And that means an average of 7.5 again, which means 15 up from this 70 value at 2 seconds. Which brings us to 85, and that's about here. Oh, a little lower than that. There. Okay. Now what about 4 to 5? 4 to 5, we go the exact same 22.5 as found over here. Because it's 15 to 30 meters per second, averages out to 22.5. Because 45 divided by 2. And that'll be 7.5 past this gap of 15 up to 100. So 107.5 will put us up to about there. Yes, when you do a diagram, you could potentially end up using a ruler and measuring it to scale and all. But when you're doing a sketch in class, generally you're pretty much going to be eyeballing a lot, if you have a grid to eyeball off of. If you don't, please don't try this. Ever. So this is a matter of plotting points to make a curve, and then the rest is just a straight line because the velocity is constant. So 6. Well, we end up going a total of from 15 meters per second to 45 meters per second over 2 seconds is average of 30 meters per second for 2 seconds. That's 60 meters over this value here, which was 85, which is 15 short of 100, and 60 is 45 more than that. That's about here. Quick and effective mental math is also very nice to use, even if it's not as straightforward as might be appreciated, like a calculator would give you. Now, 6 to 8 seconds. We're moving at 45 meters per second, and we start at 145 meters. That's going to be a total of 90 meters over 2 seconds. Starting at 145 is 235, which is up here, more or less. Okay, a little bit more than that. And then we connect these with a curve, or rather a line for this bit. As said before, use rulers wherever you can, and the rest, well, take your best stab at it and produce as smooth a curve as you can. Make sure that it fits through the points you plotted. Alright, in summary, the area under an acceleration time graph gives you the velocity change of the object. And given one type of motion graph, you can find the other 2 types of motion graph. So acceleration time, velocity time, and position time being the 3 types. Now what happens if you have to, instead of going from position time and finding velocity from that and finding acceleration from that, you have to go in reverse. Well, you have to have some set values. Otherwise, you end up with the, okay guys, I step on the gas. Where am I? Am I at the reference point, or am I already very far from the reference point? And how fast am I going anyway? Am I stopped at the reference point, stopped far away from the reference point, stopped not so far away, or am I moving at any one of these places? Or am I even pointed the other way from the positive direction and then stepping on the gas? Although that's kind of interesting because that implies that your car is sliding backwards or still coasting backwards in reverse, which should be prevented by you switching to a forward gear if your acceleration is positive. But that's where the metaphor kind of breaks down, so please don't go too philosophical about it. Okay, next section, we get to discuss some more of the equations that govern kinematics. So they relate time, displacement, velocity, and acceleration. So see you next section.